Hello students. In this video, I will explain basic concepts of AC circuits. On the screen, we see a series RLC circuit, a resistor, an inductor, and a capacitor are connected in series. An alternating voltage is applied across them. Here, we are assuming the voltage to be a sine function of time. It can also be a cosine function of time, but the analysis will anyway be similar. Now, if we take the terminals of the voltage source as A and B, during positive half cycle, A will be of positive polarity and B will have negative polarity, and the current in the circuit will be in the clockwise direction. During the negative half cycle, A will have negative polarity, B will have positive polarity, and the current in the circuit will be in the counterclockwise direction. But the current in the circuit need not be in phase with the voltage applied. Okay, so you might ask, what does it mean when I say that the current need not be in phase with the voltage applied? So I mean that the current need not go hand in hand with the voltage applied. Again, what does it even mean? So whatever current we get in the circuit, when I say that they don't move hand in hand, this is what I mean. Assume that the voltage reaches its maximum value, a particular value. In this case, we are taking the maximum value at a particular moment in time. The current need not reach its maximum value at that moment in time. Okay, so it can reach its maximum value either before or after the voltage has reached its maximum value. Okay, so there is a phase difference between current and the voltage. Now, this phase difference is obviously in terms of angles. Uh, so that means the current that we get in the circuit will be of this form. So you will have some maximum value. Okay, it will be a sine function, but the phase of this will not be omega t. Okay, so the phase will be different. Okay, so the phase will be omega t either plus or minus phi, where phi is the phase constant. Now, in our discussion, we can either select plus or minus, but I will be going with minus. Okay, so the current is assumed to be some maximum current into sine omega t minus phi. So here Im is the maximum current and phi is the phase constant. Our goal in this analysis is to find the values of the maximum current and the value of the phase constant. For that, we are assuming that we will be given the value of resistor, inductor, and the capacitance, and also the maximum value of the voltage applied is known, and the angular frequency of the voltage variations is known. And you might also know how to relate omega with the natural frequency of variation, which is omega is 2 pi f. So in AC circuits, we are saying that the current will not move hand in hand with the voltage. And so obviously, if you look at the current function, you can easily guess that the current not only changes the direction, it also changes the magnitude. Okay, so sometimes it is in the clockwise direction, at other times it is in the counterclockwise direction. Below the circuit diagram, voltage and current graphs are shown. Here I have assumed a particular value for the phase difference. I have taken the phase difference to be 30 degrees or pi by 6 radians. Okay, so if you look at the graphs, we can easily notice that the current reaches its maximum value a little later after the voltage has reached its maximum value. So if I consider voltage reaching its maximum value as one event and the current reaching its maximum value as another event, there is a fixed time difference between these two events. And then that time difference is usually expressed in radians as this phase constant or phase difference. Now, I will talk about a very important geometrical construct. It is known as a phasor. Now, what exactly is a phasor? In my classes, I always tell my students that phasor is a cool name for a superhero. We should name the next Avenger as a phasor. I think it'll be very nice. Okay. Again, jokes apart, what exactly is a phasor? I put little notes at the bottom of the screen and then two arrows. A phasor is simply a rotating vector. Okay, so it's just an arrow that rotates in space about a point. Here, the yellow arrow and the green arrow, you can visualize that they are getting rotated about the origin here. Now, this rotating vector is very useful in describing quantities that vary sinusoidally. And in our discussion on AC circuits, we have started seeing that voltage is a sine function of time, the current is also a sine function of time. So, this geometrical construct, the phasor, will be very useful in analyzing the current in the circuit. So, right now, you may not appreciate if you are looking at this concept for the first time, but as we go on with our discussion, I am very hopeful that you really appreciate the usefulness of this idea. Okay, so let's take a look at the voltage phasor. So, we have an arrow representing the voltage phasor. So the length of the arrow is proportional to the maximum value of the voltage here. So the yellow arrow, the length ideally is proportional to the maximum value of the voltage. At some moment in time, let's say if we are taking the time as t right now, the arrow makes an angle omega t with the horizontal line. So horizontal line is taken as the reference line. The x-axis is the reference line. And then at this moment in time, if we want the instantaneous value of the voltage, all we have to do is take a projection of this vector onto y-axis. So that will give us the instantaneous value of the voltage. And we can do the same thing for the current phasor. Okay, so the current phasor right now is making an angle omega t. Oh, sorry, what happened? Let me go back. Okay, so the current vector is making an angle omega t minus phi at this moment in time. So if we want the instantaneous value, all we have to do is take its projection onto y-axis. So that gives the instantaneous value. So you can see from these two diagrams that this vertical distance is im. Okay, im is the magnitude of the length of the arrow, or we can say the length of the arrow is proportional to the maximum value of the current, or for the voltage phasor it is the maximum value of the voltage. Okay, one very important point here, these two arrows are rotating. Okay, so what is the speed of that rotation? Okay, so each of these arrows will be rotating with an angular velocity omega in the counterclockwise direction, and this angular velocity is equal in magnitude to the angular frequency of the voltage and current variations. Okay, so as these arrows rotate, If you take a vertical projection, a projection onto y-axis, we get the instantaneous values, and the length of the arrow is proportional to the maximum value of these physical quantities. Now let us see how to find the maximum current and the phase difference between current and the voltage applied. Note that the same current passes through each of these circuit elements, and the usual strategy is to find the potential drop across each of these circuit elements and combine them. We denote VR to be the potential drop across resistance, VL as the potential drop across the inductor, and VC is the potential drop across the capacitor. So R, L, and C are used as subscripts here. Potential drop across the resistor. The current I is Im into sine omega t minus phi, where Im is the maximum current in the circuit, phi is the phase difference. So by Ohm's law, the potential drop VR across the resistor is simply the product of current and the resistance, and this will be written as Im into R into sine of omega t minus phi. Okay, so here what is generally done is, if you take the product of Im into R, it is written as the maximum voltage drop across the resistor. Okay, so that's a constant value. The product is a constant value. So if I consider this as VR, let's say I'll put M to denote maximum, into sine of omega t minus phi. So here VRM is simply Im into R. Okay, let's understand one thing here. If I take a look at the current that is passing through the resistor and the voltage drop across the resistor, both have the same sign function. Okay, so the phase is same, omega t minus phi. So here we can say that the current and the voltage drop across the resistor are definitely in phase with each other. So when the current reaches a maximum value, the voltage drop across the resistor will also reach a maximum value exactly at the same time. So what we will do is, we will just use phasors to represent the current and the voltage drop to get a better idea. If we look at the diagram, there are two arrows. One arrow is used to represent the current phasor, and the other arrow is used to represent the voltage drop phasor across the resistor. Here Im is the maximum current and VRM is the maximum voltage drop, and it is expected that the length of each of these arrows is proportional to this maximum value, and both the arrows are rotating in the counterclockwise direction at an angular velocity omega. Okay, so since there is no phase difference between these two physical quantities, the arrows are shown coinciding with one another, and the angle made by these arrows with the reference line, the x-axis here, is same, omega t minus phi. Now to get the voltage drop across the inductor, we take the help of Faraday's law. The voltage drop here by Faraday's law, I'm writing the magnitude here, It is the product of inductance L and the rate of change of current with respect to time. Okay, so di by dt. We don't have to worry about the minus sign here, because the minus sign simply indicates that the inductor is fighting against the changes in current. So we are okay to get the magnitude of the voltage drop. We are anyway calling this the voltage drop. So here L and then di by dt, Im is constant. When you take a derivative of sine, we get cos, and we have a composite function here. So we need to take the derivative of omega t minus phi. So we get omega. I'm writing that in front of the cos function, and phi is constant, so that's 0. So we can leave it like this. And here it is customary to write current upfront, and then you take the combination of L and omega, you write it as omega L. That's the practice. And okay, now if I write the cos function using sine function, we had some very good let's say insight, or let's say result here. So I can write this as sine of omega t minus phi. I'm assuming everyone is okay with this, right? So sine, let's say, okay, the font is too big. Okay, so sine of theta plus 90 or pi by 2 is cos theta. Okay, so I'm using this identity to write the cosine form back in the sine form. So we will have plus pi by 2. Okay, now let us compare the current function. Okay, so in the current function we have sine of omega t minus phi, and for the voltage drop across the inductor, we have phase as, we are using the same sine function, but the phase is omega t minus phi plus pi by 2. So this pi by 2 is the phase difference between the current that is passing through the inductor and the voltage drop across the inductor. And because we have plus pi by 2, we can say that the voltage drop across the inductor is going to be 90 degrees ahead of the current. So it is leading current by pi by 2 radians. That is one thing. The second thing that is important to note here is the combination of omega and L. Okay, so the combination of omega and L, if you observe closely, we know that sine will give us a number. We are looking at a voltage drop. So this combination should be in volts. The product of current and omega L must be in volts. So clearly the combination of omega L must have units of ohms, must be in ohms. But we don't call this combination a resistance, because in a resistor, whenever you have current, there is a loss of energy. Okay, so resistor is used to let's say denote energy consuming devices, right? So here when you have a coil, we are assuming that it is an ideal coil. Okay, so it's an ideal inductor. It reacts to the changes in current, but there is no loss in energy. Okay, so for those reasons, this combination omega into L is known as inductive reactance. Okay, so this is known as inductive reactance. Reactance. The symbol is X sub L, that is what is used here. x sub l, and then that will be omega l. The units are ohms, but it is known as inductive reactance. Okay. So now using this, we can write the potential drop across the inductor as Im into XL into sine of omega t minus phi plus pi by 2. Okay, so we can take this one step further now. So take a look at this combination Im into XL. Okay, so this is clearly the maximum potential drop across the inductor. So this combination, you can say, you can write it as VLM, which is the maximum potential drop across the inductor. So we can write this as VL will be VLM into sine of omega t minus phi plus pi by 2. Okay, so there is a reason why I'm leaving this as it is, because we can compare this against the current that passes through the inductor. Okay, so if you look at the current function, so we have maximum current and multiplied by sine of omega t minus phi. In the phasor diagram, the phasor used to represent the voltage drop across the inductor, this yellow vector, is drawn 90 degrees ahead of the current phasor. And each of these rotating vectors, the phasors, rotate in the counterclockwise direction with the same angular velocity. So this phase difference between the current vector and the voltage vector remains constant throughout. Okay, so just keep that in mind. So that will be useful to us in the coming let's say discussions. Now, to get the voltage drop across the capacitor, first we need to get the charge that is going to come onto these plates, and then use the charge, basically divide the charge by capacitance to get the potential drop across the capacitor. Okay, so we know that the current is a function of time. So the charge can be obtained by integrating this current function. So it is integral of I dt. Okay, so if we substitute the current function, Im sine of omega t minus phi dt. Okay, so here the charge that is coming onto the plates will be Im is constant, so we can pull it out. The integral of sine would be, I guess it is minus cos, so minus cos of omega t minus phi. And again, I suggest you revise the integrals of functions here. I think if you go back to your substitution technique, you will realize that when you take an integral of a composite function, you divide by the coefficient of time here. So we will have to divide this by omega. Okay, and what do we have? This is dt. Yeah. Oh, why am I writing dt? So we are done with that. Okay, so okay. Now the potential drop across the capacitor will be charge divided by capacitance. So here we can write this as Im. I'm combining omega and c together. So I have 1 over omega c. Okay, again here let's write this cosine function into sine function. So to do that, I think we can use the trigonometric identity. Okay, so sine of theta minus pi by 2 is minus cos theta. So if I use this, I can write this cos function as sine of omega t minus phi minus pi by 2. Okay. Now let's look at the phases of the current function and the voltage function. So the phase of current is omega t minus phi, while the phase of voltage drop across the capacitor is omega t minus phi minus pi by 2. Okay, so what is this telling us? Here, the voltage drop across the capacitor is lagging behind the current by 90 degrees or pi by 2 radians. Okay. Okay, so we will see that in our phasor diagram as well. And again, look at this combination here. Okay, so similar to what we did for the inductance, for the voltage drop across the inductor, if I take this combination 1 over omega c, it must have the units of resistance. But again, we don't call this resistance for the same reason. Okay, so the capacitor is not an energy consuming device, it is an energy storing device. So this combination is known as capacitive reactance. Capacitive reactance. Okay, xc is used to represent this. So xc is 1 over omega c. Now if I again combine this with the maximum current, the voltage drop across the capacitor will be written as Im into xc into sine of omega t minus phi minus pi by 2. Again, let's combine Im and xc. So that will be our maximum voltage drop across the capacitor. So the voltage drop across the capacitor can be written as maximum voltage drop across the capacitor into sine of omega t minus phi minus pi by 2. So please take a note of this minus sign, be very careful here. And let's write the current function here as well. So I is Im into sine of omega t minus phi. Okay, so in the phasor diagram, if you look at the arrow that is used to represent the voltage drop across the capacitor, it is drawn showing let's say behind the current vector. Okay, so the current vector is making an angle omega t minus phi, and the arrow representing the voltage drop across the capacitor is behind the current arrow by 90 degrees. Okay, and again each of these arrows rotate with the same angular velocity omega. Now is the time to combine all the phases that we have drawn. Okay, so let's take a look at the phases again. So let's revise them. Okay, so initially we drew this current phasor. So here we have this current phasor. The current phasor is a rotating vector representing the current in the circuit. Okay, so this arrow makes an angle omega t minus phi with the reference line. And we had the voltage drop across the resistor, and this is the phasor representing the voltage drop across the resistor. And we saw that there is no phase difference between the current in the circuit and the voltage drop across the resistor. That is why these two arrows coincide with one another. Okay, so now if we take a look at the voltage drop across the inductor, we saw that this arrow must be 90 degrees ahead of the arrow representing the current. Why? Because the voltage drop across the inductor is always 90 degrees ahead of the current in the circuit. Similarly, not really similarly, I mean, when you look at the voltage drop across the capacitor, the arrow representing the voltage drop across the capacitor, this arrow must be shown 90 degrees behind the arrow for the current. Okay, again, why? because the voltage drop across the capacitor is always behind the current by 90 degrees. Okay, so I hope we are clear here. And now what we will do here is, instead of working with all these trigonometric functions, generally the phasor diagrams are used to combine these voltage vectors, okay, combining these voltage phases, and then that would give you the voltage applied. Okay, so we will get the phasor for the voltage applied. Okay, so now let us take a look at them here in one single diagram. So here in the same diagram I have all these four phases. We have this current phasor, we have the phasor for the voltage drop across the resistor, we have the phasor for the voltage drop across the inductor, and we have the phasor for the voltage drop across the capacitor. Okay, one important observation here, we are saying that these are rotating vectors, and again you can just simply use your understanding of vectors. Okay, so what do I mean by that? You can take these vectors, feel free to add them as you added vectors earlier. So they are our good old vectors. Okay, so we don't have to hesitate uh, when we have to do vector addition here. Okay, and what else is happening? So if you look at these four arrows, they are rotating in the counterclockwise direction at an angular velocity omega. So that means wherever they are, okay, so wherever they are, the angles between the vectors, okay, so if you take any two vectors, the angle between them will always be constant. For example, if I take the voltage drop across the resistor and the voltage drop across the inductor, the angle between them is 90 degrees, and then that will always be 90 degrees wherever these two vectors are in the plane. Okay, so that is very important to note. Okay, so the same thing holds good for any two vectors. So because this is happening, what we can do is, if we take this reference line, let's say our x-axis is the reference line, the current vector is making an angle omega t minus phi. So we can take that angle omega t minus phi, okay, so omega t minus phi, we can take that angle and then reset that to 0. Okay, so we can reset that to 0. So if I reset that to 0, what am I doing here? I'm taking this current vector and then I can just write it along the horizontal line, along the x-axis. Now, if you want for a series RLC circuit, you can take this current vector as the reference vector. Okay, so because in a series circuit, the current is same through each of these elements, resistor, inductor, and the capacitor. So instead of taking x-axis as the reference line, we can take current vector as the reference vector. And then we have this voltage across the resistor. Okay, voltage across, sorry, what is happening here? Okay, so voltage across the resistor will be along the current vector. Voltage across the inductor will be conveniently along the y-axis, positive y-axis, and voltage across the capacitor will be along the negative y-axis. So this is super helpful when you actually draw like this. And then again, coming back to the vector addition, the voltage drop across the inductor is 90 degrees ahead of the voltage drop across the resistor, and the voltage drop across the capacitor is 90 degrees behind the voltage drop across the resistor. Okay, now forget about voltage drop across the resistor for a moment. If you consider the voltage drop across the inductor and the voltage drop across the capacitor, okay, so the arrows representing these two voltages are 180 degrees out of phase. Okay, so they're pointing in opposite directions. So when we take a vector addition, okay, so we will simply have to take a difference here. So this arrow represents the vector sum of the voltage drop across the inductor and the capacitor. And then if I combine that with the voltage drop across the resistor, we must get the voltage drop, sorry, we must get the voltage applied. Okay, so this phasor right here must represent the voltage. What am I saying? Yeah, this phasor must represent the phasor for voltage applied. Okay, so if the horizontal line, okay, why am I erasing this? One moment. Okay, if the horizontal line is corresponding to omega t minus phi, and we know the phase of voltage applied is omega t, right? So that means, how do I get omega t? I just have to add phi to omega t minus phi. So I'm adding phi here to omega t minus phi. Remember, the horizontal line corresponds to omega t minus phi. So if I add phi, I get the phasor for the voltage applied. Okay, and again, if you take the vector sum of these maximum voltages, we should get the maximum voltage applied. Okay, so this is the crucial observation here, which is very very important. And then I think it's very nice if we can keep this in mind. The problems are easy. Okay, and again, remember, we are yet to get the maximum current and the phase difference. Okay, so I think we are one small step away from that. Okay, now let's keep this in mind. The central idea here is, if you consider these maximum voltage applied and the maximum voltage drop across the resistor, maximum voltage drop across the inductor, maximum voltage drop across the capacitor, and if you treat them as vectors, okay, I mean, it's not very nice to write like this, but let's say you treat them as vectors. So if you treat them as vectors, the vector sum of these three is simply going to give you the voltage vector, or the vector for the applied voltage. Okay, so the vector sum of the voltage drop across the resistor, again here you have to understand that we are not taking, again keep this in mind, we are not taking the instantaneous voltages, we are considering the maximum voltages. Okay, so if I take the maximum voltage applied, maximum voltage dropped across the resistor, maximum voltage drop across the inductor, maximum voltage drop across the capacitor, if I take them vectorially, their vector sum is going to give you the maximum voltage drop applied. Can I say maximum voltage drop applied? No, 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 I can't say that. It gives the voltage applied, maximum voltage applied. Okay, so this is very, very important. Just keep this in mind. Finally, we have reached the step where we can find the value of maximum current in the circuit and the phase difference between the current and the voltage applied. Okay, so we know that the maximum voltage drop across the resistor can be written as current. Okay, what am I doing? Okay, 1 second. Yeah, so it's a product of current, maximum current, and the resistance. So likewise, the maximum voltage drop across the inductor is the product of current and XL. Voltage drop across the capacitor maximum value is current and XC. Okay, now when we use Pythagoras theorem to get the uh, magnitude of the resultant of these three voltage drops, we should get the maximum value of the voltage applied. Okay, so this we have seen. So if we substitute these values in the expression or the equation that we just obtained, which is the square root of VRM square plus VLM minus VLC whole square, this should be maximum voltage applied. So now let's substitute these values here. So what should we get on the left hand side? We have Im square into R square. I can take Im out, M square into XL minus XC whole square, and then this should be equal to Vm. So from here we get the maximum current in the circuit will be maximum voltage applied divided by square root of R square plus XL minus XC whole square. Okay, so this quantity right here in the denominator, this is known as impedance of the series RLC circuit. Okay, so it has a symbol Z. So impedance Z. This is square root of R square plus XL minus XC whole square. So we can write the maximum current in the circuit as maximum voltage applied by Z. Okay. Now let's get the phase difference. If we look at the triangle here, the triangle OAB, this is known as an impedance triangle, very helpful in solving AC circuit problems. Okay, so from here, if I write down tan of phi, okay, the font is big, let me reduce it. Okay, so if I write tan of phi, it is AB by OA. AB is proportional to VLM minus VCM. Okay, so the difference in voltage drops across the inductor and the capacitor. OA is proportional to the voltage drop across the resistor. Again, throughout we are using only maximum values, so keep that in mind. So VLM, I can write it as IM into XL, VCM IM into XC, VRM is IM into R. So from here, if I cancel IM, I get tan of phi as XL minus XC by R. Okay, so now we have both the phase difference and the value of maximum current. Okay, so one note here, the angular frequency of the voltage variations, the applied voltage variations, omega, is constant, and the values of resistance, inductance, and the capacitance, they are also constant. So if we look at the ratio on the right side, XL minus XC by R, this will also be constant. Okay, so what does that mean? That means tan phi is constant and the value of phi is constant. So there is a constant phase difference between the voltage applied and the current in the circuit in a series RLC circuit. Okay. Now, just a recap of the important results we have obtained. The maximum current in the series RLC circuit is obtained by dividing the maximum voltage applied by a value known as impedance Z. Okay, so this is one thing. The second result is the tan of phase difference between the current and the maximum voltage applied. Tan of phi will be XL minus XC by R. Okay, so these two are very, very important. Okay, now in order to compute the maximum current and the phase difference between the current and the voltage applied, we need XL and XC. So how do we get XL, the inductive reactance? Okay, and let me reduce the font. So sorry there. Okay, so XL is product of omega and the inductance, and XC will be 1 over omega into C, and both XL and XC are in ohms. Okay, so this is just a small recap. Okay, so next what we will do is we will try and get an understanding of power supplied by the voltage AC supply and the power consumed. So we should note that the inductor and the capacitor, there is no energy wastage in those elements because we are assuming these elements to be ideal. So whatever power that is getting supplied on an average should get consumed only in the resistor. Okay, because resistor is the element that is consuming the energy. Now let us look at the time based average of the voltage applied. So we can take one cycle here, one cycle of voltage variations, and if we need the average value of the voltage applied, we should get the time based sum of the voltages. So the voltage is varying as a function of time, so you can take tiny intervals, and if you multiply voltage with those tiny intervals, let's say dt, we get the time based sum for the tiny time interval dt. And then if we integrate this, okay, let me write that properly. So if you integrate this, I think sometimes I find it difficult to write the integral symbol. So 0 to t. So for one complete cycle, we get time based sum of the voltage, and then if you divide by time, we should get the time based average. So intuitively, and again from looking at the graph, we can say what this value should be, because when you take the sum of the voltage for a complete cycle, you see that half of this cycle is above time axis. Okay, so this area will be positive and half of the cycle is below time axis, and then this area will be negative. So when you add these two areas, we should get 0. So the average value should be 0. But again, how is that useful? It is not at all useful, because we can't really say that the voltage applied is on an average 0, because that doesn't it's true mathematically, but it's not useful for us because we continuously get the voltage. So for a cycle, that is true, but it's varying rapidly, so we do have voltage supply. So mathematically we can get the answer, evaluate, and then confirm that it is 0. But if you are okay with this intuitive understanding that the average voltage for one complete cycle will be 0, we don't have to do that. But again, let me do that because sometimes in some of the problems you may not be given a nice sine curve. Okay, so we have other types of voltage variations, like so you have some sort of a square waveform or a triangular waveform. Okay, so in such cases, I think the process is still the same. Okay, so you get a time based sum for a complete cycle or for whatever time interval they are seeking, and then you divide by that time interval. So for that reason, I think we should still go ahead and then complete this integral. So let's do that. So here we have v is vm into sine of omega t and dt. So I can take this time out of the integral. Let's say no, it's anyway out of the integral. So I'm just putting it at the side. Okay, vm is constant, so we can take it out by t, and then integral of sine, we know it is cos omega t, and then again we have a composite function, so we need to divide by the coefficient of time, so by omega. That's it, and then we just have to substitute the limits. Okay, so when we substitute the limits, let us also substitute omega in terms of the time period t. Omega is 2 pi into the natural frequency, and then we know natural frequency is reciprocal of time period, so 2 pi by t, so we can substitute this. So vm by t, and then cos of omega. I think this omega in the denominator we can pull it out. So omega is 2 pi by t and into t minus cos of 2 pi by t into 0. Okay, so we have vm by t omega. Okay, so the first term we have cos 2 pi. Cos 2 pi is 1. And the second term we have cos 0, so that is 1. So we have an average value of 0 for the voltage applied. But again, like I said, we don't use this value. We are more interested in a value known as RMS value. Root means square value of the voltage applied. So we will look at that soon. Okay, so now if you go ahead and then compute the average current for one complete cycle, you should again get 0 here. Okay, so I will leave this as an exercise to you. It should be easy to verify this. Again, intuitively, if we take a look at the half of the cycle which is above time axis, you see the area here which is positive. This area should exactly be equal to, let's say, this area plus this tiny negative area here. Okay, so I'll leave the integral to you. Like I mentioned a little while ago, instead of average current or average voltage, in the analysis of AC circuits, we are mostly interested in the RMS currents and RMS voltages. Now, what is this RMS current? So let's compute that. And again, so let's not do too much of maths here. Let's see. Okay, so if I look at this RMS current, maybe one thing that you can do is you can start looking at this from the end. Okay, so if you look from the end, so you will see that you have S, which stands for square. So we are going to square first, and then M is mean. So we're going to take the average, and then R stands for the square root. So the RMS current here will be, first we're going to square the current. Okay, and we're going to take the average of this current, and we take a square root of this. Okay, so now let's see what we have inside the square root. So we have im square and sine square, okay, sine square omega t minus 5. Okay, now I can take im is constant, and then you have a square inside, so I can take that out, and Okay, so one small mistake. So I'm supposed to take the average of this. Okay, so let me indicate that. Okay, so I need average of sine square omega t minus phi. So I can take it outside anyway. So I am taking the square root of average of sine square omega t minus phi. Okay, so we're just mentioning it like this. Usually we can use a square, I think angled brackets, not square brackets, angled brackets. So this is what is normally used. Okay, so if you put these angled brackets, this means the average of this value. Okay. One small note here. See, omega is usually large. Okay, so the variations, the current variations are very, very rapid. Okay, so we consider, let's say, this RMS value for many cycles. You can ignore the partial cycles. Okay, so you can say that we have integral number of cycles, let's say. Okay, and we know that sine theta plus cos theta is 1. What did I say? Sine theta plus cos theta is 1. So bad, so bad. Okay, I think you know what I meant. Okay, so I meant sine square theta plus cos square theta is 1. And we know that sine square theta and cos square theta in terms of areas. Okay, so you will have same areas. Uh, and then the average value of sine square theta and cos square theta is same. So if I take the average value of sine square theta for a cycle or many cycles, these two will have the same average values. Okay, so angle bracket again means average values. So because they have the same average values, I can say that the average value of sine square theta should be half. Okay, or you can go ahead and then compute the average of this trigonometric function sine square omega t minus phi using the integral, but I think this is sufficient for us. So I'm going to substitute half here. So we have half, and then we will get a relation between the RMS current and the maximum current. So this will be IRMS will be IM by root 2. So this is again an important relation to keep in mind. Okay, this is also true for voltages. I mean, if you have the maximum voltage, if you take that and then divide it by root 2, you will end up having RMS voltage. Okay. Now that we know how to calculate the maximum current and the phase difference between the current and the voltage, let's look at the average power supplied by the AC source and the average power consumed by the resistor. And inductor and the capacitor, they don't really waste any energy. So we are assuming that our inductors and capacitors are ideal. Okay. So if I am looking at the average power supplied by the AC source at any time t, okay, so we are looking at any time t, or you can say instantaneous power supplied. So P, I'll just write SUP, power supplied. This will be simply the product of voltage at that time and current. Okay, so voltage supplied multiplied by current. Similarly, average power consumed at any time, if I write this down as well. Okay, I'm doing these at the same time. So we will write it as P con. Okay, so CON for consumed. So this will be square of current multiplied by the resistance. Okay, so now let us substitute these values here. We know the current function and the voltage function from here. So we have the voltage function, which is V is equal to Vm sin omega t, and then we have the current function. Okay, so we know the maximum current, we know the phase difference, so we have everything now. Okay, so let's substitute these values here. Okay, so V will be, okay, let me change the font again. Okay, yeah, so this will be Vm into sine of omega t multiplied by Im into sine of omega t minus phi. Okay, so here we need to use a trigonometric identity. I am hoping everyone recalls this. So we know that the product of sine A and sine B can be written as cos of A plus B minus cos of A minus B divided by 2. Okay, so this entire thing you need to divide by 2. Okay, so we can use this here. Okay, so what will be the power supplied? What is happening to this font? Let me change it. Okay. So what is the power supplied by the AC source? Okay, so here I'm trying to bring these maximum values together, Vm and Im, and then we are left with two sine functions. And then just realize that omega t can be treated as A. Okay, so that's A. And then omega t minus phi can be treated as B. Okay, so if you do that, I guess I might have made a mistake. Okay, so I think the mistake is this. I don't think it is cos of A plus B minus cos of A minus B. I think it is, let me correct that. I think it is cos of A minus B, and then here we should have A plus B. Okay, so you can verify that. Okay, so now what is cos of A minus B? So we will have, I think this the entire thing will be divided by 2, so I'll write that up front. Array. I'm so sorry. Okay, so I divide this by 2 and I will have cos of A minus B. So omega t minus minus it will become plus. So I'll have cos phi, and then minus cos of, I need to add them. So 2 omega t minus phi. Okay, so this is the power supplied at any time t. Now let's take a look at the power consumed at any time t. So here we are substituting the current function. So we'll have Im square, and we have sine square omega t minus phi, and then I'm writing r upfront. Okay. Now again, so if you really look at the average power supplied, okay, we are interested in average power supplied, so we need to get the average of two quantities. Okay, so this factor up front is anyway constant. Okay, so that will anyway be there. Okay, so if you have values which are constant, so the average will be that constant value, so we don't have to worry about that. And even cos phi is constant, so we don't have to worry. So the varying quantity is the second term. Okay, so we have already seen that the average value of sine omega t minus phi is 0, and then here we have cos omega 2 omega t minus phi. It's just that you can consider that you have a function with twice the angular frequency, and the average value of this should also come out to be 0. So you can verify this. I will leave this calculation to you. So if you get the average value of this function, that should be 0. So that said, what do we have now? Okay, so we are left with only the constant terms. So the average power supplied, I'm using the angle brackets here. So the average power supplied, okay, I think that font is chasing me. The average power supplied will be simply Vm into Im by 2 multiplied by cos phi. Okay, so that's the average power supplied. So let's put a box around that. This is very important. Okay, and what is the average power consumed? Okay, we have again, we need to get the average here. So I'm placing angular brackets here. Okay, so the constant values I can just take out, and then we have already seen the average value of sine square omega t minus phi is 2. So the average power consumed will be I square of maximum current multiplied by R. Okay, so this is again important for us. Okay, so here one very important observation. Okay, now we can actually show that because the inductor and the capacitor, because they are not consuming any energy, on an average, the average power supplied by the AC source must be equal to the average power consumed. Okay, so I think let us show that. Okay, so this is what I am claiming. So the average power supplied, this must be equal to the average power consumed by the resistor. Okay, so this is of course by the supply, by AC supply, and this is by the resistor. Okay, so let's take a look at this one. Okay, so before I show that these two powers are equal, I think I need to redirect your attention to a mistake that I have made. I think a little while ago I did not divide. I said the average value of cos square omega t minus phi is half, but I forgot to divide by 2. Okay, so the average power consumed by the resistor will be I square m into R divided by 2. So just please note that. Okay, so now let's take a look at this now. Okay, so here we need to show that the average power supplied is equal to the average power consumed. We can show this by taking a look at our impedance triangle. So if you take a look at the impedance triangle, so this is our impedance triangle. Okay, so OAB. So OB, that phasor has a length which is proportional to Vn. Okay, so the phase difference is phi, and then OA has a length which is proportional to, so VR maximum. Okay, now we can say that, okay, so we can say that VR maximum is equal to Vm into cos phi. Okay, so what is VR maximum? VR maximum is product of maximum current and resistance. So that will be Vm into cos of phi. So in this expression, if I take Vm into cos phi, I can write the power consumed as, okay, so the power power supplied, not consumed, power supplied, I can write it as Vm into cos phi will be Im into R. I have Im and then we are dividing it by 2. So this will be square of maximum current into R by 2. So now look at the expression that we have for the power consumed. So in a series RLC circuit, again, I think this is true when we take this assumption that the inductors and the capacitors are ideal, and then I think for our purpose that's true. Okay, unless they state it otherwise in a particular problem. Okay, so in that case you can separate out the resistance part, but for the current discussion, so we can say that on an average the power supplied is equal to the power consumed by the resistor. We can use a relation between RMS quantities and maximum quantities to rewrite the average power supplied and the average power consumed using the RMS values of current or the voltage. Okay, so we know that Vrms is V maximum by root 2. So, and the RMS current is maximum current by root 2. If I use this in the first expression, the average power supplied, I can write this as, okay, this is average power supplied. Okay, so V maximum will be Vrms into root 2. So we can write this as root 2 times Vrms, and maximum current is root 2 times Irms and cos phi divided by 2. So root 2 times root 2, that's 2. So we can write the average power supplied as Vrms multiplied by Irms into cos phi. The same thing we can do for the other quantity. So if I substitute maximum current as root 2 times Irms, we can easily notice here that the average power consumed will be I square RMS into R. So if we are planning to use the RMS value instead of the instantaneous current value or the maximum current value, I think the power consumed expression, I think it's the same as power supplied value. You can use this expression to remember this. Okay, so I square RMS R, that's I think very close to the power consumed by a resistor in a DC circuit. Okay. Okay, so one important definition here, if you look at the expression for average power supplied, we have Vrms multiplied by Irms, and you have a quantity, a constant quantity, cos of the phase difference. Now, depending on the values of resistance, inductance, and the capacitance, the phase difference between the current and the applied voltage varies. So the power supplied also varies. Now the power supplied is maximum when the value of this factor cos phi is 1. Okay, so for maximum power supplied or power consumed, okay, for maximum power supplied, average power supplied, or average power consumed, cos phi is 1. This will happen when the inductive reactance and the capacitive reactance have the same value. Okay, so for those reasons, it's a factor appearing here, so it's known as power factor. Okay, so this quantity is known as power factor, so it's important to keep this in mind. Now let us solve a problem using what we have learned so far. We have a series RLC circuit here. The resistance, inductance, and the capacitance is given. The voltage supply is given. Here, one small note. Sometimes in problems on AC circuits, you might be given a voltage function specifying everything. Okay, so with the maximum voltage and then sine of omega t, where the angular frequency is mentioned, or they just indicate the voltage number and the angular frequency. So whenever you are given a voltage number without a sine or cos function beside it actually means that the particular value is of RMS type. Okay, so all measured quantities, because if you are using a meter to measure any voltage drop between 2 points and the current in an AC circuit, it is always the RMS value. The meters are designed to measure RMS values. So just keep that in mind, that's very important. Okay, now for this problem, we are trying to find the RMS current value and the maximum voltage drop across the resistor, inductor, and the capacitor. And again, we can verify that the vector sum of these three voltages amounts to the maximum voltage applied. And also, we will try and find the average power supplied or average power consumed. Okay, so we have to start here, first finding the inductive reactance and capacitive reactance. So what is inductive reactance? XL. This is omega L. Omega is 1000. L is given as 6 millihenry. So that's 6 into 10 to the power minus 3. So we have 6 ohms. And capacitive reactance XC. This is 1 over omega C. So 1 over omega is 1000. C is 500 into 10 to the power minus 6. So if you look at the denominator, I think this will be 0.5. So that should give us 2 ohms. Okay, so now using XL and XC and of course R, let's get the value of the impedance. So impedance is square root of R square plus XL minus XC whole square. So R here is 3. Okay, so 3 square plus XL is 4. I think XL is 6. XL is 6 and XC is 2. Okay, so that's conveniently 6 minus 2, 4. 4 square. 4 square plus 3 square, that's 9 plus 16, so 25. So the impedance of the circuit is 5 ohms. So using this we can get the maximum current. So maximum current in the circuit will be V maximum by Z. So what is V maximum? 100 root 2. So 100 root 2 divided by 5. So that should give us 20 root 2 amperes. And we want IRMS. So what is the RMS current value? This is maximum current divided by root 2. So that should give us 20 amperes. Okay, so we have RMS current. So our first part is done. Okay, so how do we get the maximum voltage drop across the resistor? So V R maximum. So we know this is maximum current multiplied by resistance. So maximum current is 20 root 2. The resistance is 3. So we should get this as 60 root 2. Okay, so let's take a look at the voltage drop across the inductor, which is IM into XL. So again, maximum current is 20 root 2 amperes. XL is 6 ohms into 6. So this will be 120 root 2. Okay, so these are in volts. Now VC maximum. This will be maximum current multiplied by XC. So 20 root 2 multiplied by XC. XC is 2 ohms. So this will be 40 root 2 volts. Now let's verify whether these three values add up to vectorially. Again, it is very important. They should vectorially add up to 100 root 2. Okay, so let's put an impedance triangle here. So I'll just put an impedance triangle here. So along the horizontal line, okay, along the x-axis, we place our phasor for the voltage drop across the resistor. So this will be 60 root 2. And perpendicular to this, we will have VL maximum, right? So VL maximum is this. So VL maximum will be 120 root 2. And in the other direction, opposite to VL maximum, we have VC maximum. So VC maximum is 40 root 2. Now if we take a difference of these two, 120 minus 40, we will get, so this quantity, so this will be 80 root 2. And again, so the numbers are purposefully chosen to be nice. So here if I take a vector sum of these two, okay, so if you use Pythagoras theorem for 60 and 80, I think you should get 100. So the value of the hypotenuse here, which represents the arrow or the phasor for the voltage applied, so that will give us 100 root 2. So we have verified here that the vector sum of these three maximum voltage drops indeed adds up to the maximum voltage applied. Okay, so now let us look at how to get the average power consumed. We know that the average power supplied is equal to the average power consumed, and if we use the RMS current, the expression is very easy to remember. It is simply I square RMS into R. Okay, so what is the average current, sorry, RMS current? That's 20. So 20 square, the resistance is 3 ohms, that's 400 into 3, so that's 1200 watt. Okay, so I think we obtained maximum voltage drops. We also have the average power supplied or the average power consumed. Let us look at another problem now. We are given a parallel AC circuit. We're asked to find the values of currents I1, I2 and I. Okay, so whenever in an AC circuit problem, if they just indicate the current values I1, I2, they are always RMS values. Okay, unless specifically the maximum values are asked, we can safely take them to be RMS values. So here I1, I2 are the RMS currents. And uh, this looks like, I mean, of course, this is a parallel AC circuit, but we have to understand that this is just a combination of two series RLC circuits. Okay, so we have a lower circuit without the capacitance, and if I ignore the middle branch, I will have a series RLC circuit without the inductor. So we can solve this problem by taking it as a combination of two series RLC circuits. Okay, so when we do that, for the lower branch, to get the RMS current, I need to get XL first. Okay, so XL will be omega L. So this will be omega is 1000 into 3 into 10 to the power minus 3. So we have inductive reactance as 3 ohms. So what is the impedance for the lower branch? We will call that as Z1. Because there is no capacitor here, we can write the impedance of the lower branch as simply R square. I think I'll write it as R1 square plus XL square. So this will give us R is 4, so 4 square plus 3 square. So this will give us 5 ohms. Okay, so once we have this, what is I1? The RMS current through the lower branch will be VRMS by Z1. So VRMS divided by Z1. So this should give us, VRMS is 100 by 5, that will be 20 amperes. Okay, so we have I1. Now let's take a look at the upper branch. So upper branch has capacitor, but the inductor is missing. So here we need to get the value of XC. So what is XC? XC is 1 over omega C. So 1 over omega is 1000. C is 125 microfarads, 10 to the power minus 6. So if you look at the denominator here, I think it will be 1 over 0.125. So we can write this as 8 ohms. And for the upper branch, the the impedance Z2 is square root of R2 square. We'll call that resistance as R2. R2 square plus XC square. So this will give us, what do we have? Resistance is 6 square plus 8 square. So this will be 10 ohms. Okay, so once we have the impedance, the RMS current in the upper branch I2 will be VRMS by Z2. So that will be, VRMS is 100, impedance is 10, so we have 10 amperes. Okay, but we're not done yet, right? So we have I1 and I2. So now how do I get I? Okay, if this were a DC circuit, we would have simply added these two currents algebraically, but that would be wrong here. Okay, so that would be wrong. Okay, so what we need to do here is, we cannot, okay, since we cannot get we cannot take the algebraic currents and then say this is equal to I. Okay, so this is wrong. So instead here we need to take the vector sum of the currents. Okay, so here I've not discussed the let's say, parallel AC circuits in detail, but I think intuitively you can get the idea. In a series RLC circuit, you have same current, and the voltage applied gets divided across each of these elements. So the applied voltage is a vector sum of those voltage drops. So in a parallel AC circuit, the voltage remains same, the current gets divided. So the incoming current towards each of these branches can be obtained by taking the vector sum of the currents. Okay, so if you take the vector sum of these two currents, you should get the incoming current I here. So we can use phasors to find the phase difference between I1 and I2, and then we can get the value of I using phasors. Okay, so we cannot simply add those two values algebraically. To get the vector sum of I1 and I2, first we need to get the phase relation between the voltage applied and the current in each branch, and then we can use that phase difference to get the phase difference between the currents, and finally we can get I mean, it sounds complicated, but it is not. So let's look at how we can achieve this. Okay, so here I have already went ahead and then drew the phasor diagram. Okay, so for the lower branch, in general, when we draw the impedance triangle, the voltage drop across the resistor will be along the horizontal line, and the voltage drop across the inductor will be at right angles upwards to this voltage drop across the resistor, and the resultant is the voltage applied. Okay, so here for the lower branch we don't have the capacitor, so we have only voltage drops across the resistor, inductor, and the resultant. Okay, now when we write these voltage drops using the maximum current and the resistance or the inductive reactance, we notice that the maximum current appears as a common factor, right? So, in terms of the impedance triangle, even if I ignore this maximum current, I think the remaining factors, okay, so by themselves can create an impedance triangle, okay, which is still a right angle triangle, and then the phase difference between the current and the voltage applied will still be same if I use resistances, inductive reactances, or capacitive reactances. So instead of Im into R, my impedance triangle will simply have resistance. For the lower branch, I'm calling it R1 because that's 4 ohms. For the upper branch, I'm calling it as R2, which is 6 ohms. Now, the voltage drop across the inductor is at right angles to the voltage drop across the resistor. So it's perpendicular to this voltage drop, the phasor. So we have XL there, and then Z1 is proportional to the hypotenuse is proportional to Z1. Now, by looking at these values, we can immediately write that tan phi 1 is XL by R1. Now XL is 3 ohms, R1 is 4, and this is fairly, I think, famous angle. So phi 1 will be here 37 degrees. So similarly, for the upper impedance triangle, R2 and then XC XC is denoted by that arrow pointing downwards perpendicular to R2. Again, the same logic here. So if you look at the impedance triangle here, the horizontal horizontal arrow, its length is proportional to Im into r. The vertical arrow, its length is proportional to Im into xc, and the hypotenuse is proportional. The length of the hypotenuse is proportional to Im into z. So we can ignore again Im, and we still have the impedance triangle by just using resistances, reactances, and of course the impedance for the hypotenuse. So here, if I use the definition of tan, so tan phi 2 will be xc by r2. So what is xc? Xc is 8 by r2 is 6, so this is 4 by 3. So this is another angle. I'm hoping everyone knows this angle. So the phi 2 will be, I'll write it here, phi 2 is 53 degrees. Now these are the phase differences between the voltage applied and the current in each branch. Now for each branch, the voltage applied is common, right? So for a parallel circuit, for a parallel AC circuit, we can take the voltage phasor as the reference phasor. So if I take voltage phasor as the reference phasor, and I am just drawing it along the horizontal line. So let's say this is my voltage phasor. This is representing the applied voltage. Okay, so this is for the applied voltage. Now, if I take a look at the lower branch, it's an inductive branch. So the voltage will be ahead of the current by that phase angle 37 degrees, right? So that's the phase difference between voltage and the current in the lower branch, I1. So current is behind the voltage. So when we draw the phasor for current, we must show it, let's say, lagging behind the voltage phasor. So this arrow represents I1. So this angle will be 37 degrees. Now for the upper branch, it's a capacitive branch. So here current leads the voltage applied, and then what is the angle? It leads by 53 degrees. So we need to show that ahead of the voltage phasor. So this arrow represents I2. Now what is this angle? The angle here is 53 degrees. Now if you take a look at these two angles and then add them up, you get 53 plus 37, that is 90 degrees. So what is the phase difference between these two currents? It's 90 degrees. So that means when I use vector addition, the magnitude of I, or the RMS current that is passing through the voltage supply, will be square root of I1 square plus I2 square. We are simply using Pythagoras theorem because the angle between the currents is 90 degrees. So I1, we have it as 20 amperes, I2 is 10 amperes. So now substitute 20 square plus 10 square. Okay, so how much would that be? I think that would be 10 root 5 amperes. So that is the current that is passing through the AC supply.